Friday night to hear about dinosaurs. Yeah, I'd like to start by thanking Jay and all of the staff at ESI for making all of this possible. Really a lot of work that went into this event, and to thank them for inviting me here this evening. But in all the time that they put into this event, I got to be at a remote field site in Antarctica digging up fossils. So I think I was the lucky one in that turn of events. So this is our picture of our remote field camp where I just got back from last week in Vega Island, Antarctica. But we're not going to spend time in Antarctica today. We're going to focus on another part of the world. And with that, I'd like to start into my talk. Today we're going to talk about dinosaurs in living color and a little bit in technicolor. So if you heard Jenny Kubo's talk earlier this evening, or rather just some minutes ago, you glimpsed some of the process behind bringing dinos to life on screen. And for many of us, technicolor dinosaurs, or dinosaurs in the movies, are the only ones we know. And indeed, as long as we've known about dinosaurs, we've wondered about their appearance. We've speculated. We've colored them different hues and put different patterns on them. But we haven't had a sense of what they really might have looked like in a lot of ways. So actually, tonight I want to start with this image from your brochure, from the brochures, from our fun T-shirts. It's from a movie. It's from this giant screen films movie called Dinosaur Alive. And actually there's another star, several other stars of Dinosaurs Alive, I think, in the audience here tonight. Different scientists, not dinosaur stars. They couldn't be with us except on the PowerPoint presentation. So I want to start with this guy for several reasons. This guy fits a lot of our ideas about what dinosaurs look like. He's scaly, he's a little bit aggressive but slightly endearing. He's got this coat that's kind of a leopard print. He's kind of like a carnivore, something fierce or carnivorous. And in all of those ways, it fits with perhaps maybe our notion of dinosaurs. They're roaring, they're, if you've ever seen animatronic ones, you'd think they kind of moved like this, but whatever, they're scaly. And in fact, unfortunately, this is neither a dinosaur nor what we think dinosaurs look like. So what we have here is, in fact, a color pattern that's based on comparisons with things that are more closely related to us, like leopards and tigers and mammals, things more closely related to us. And we have this scaly pattern that we're going to look into. So if this guy, who looks so much like a dinosaur, is not a dinosaur, then what is a dinosaur? Do we really know? What is a dinosaur? So I want to start with that question because it turns out that what is a dinosaur is a really key question to figuring out what dinosaurs look like. So for this next section, I'm going to need your help. So I hope you guys are still awake. I can see they've dimmed the lights, your kind of outlines out there. But I want to start with our knowledge of dinosaurs. So if we look at the name, for example, we see dino related to fearful, great, terrible, leopard print, and soar, this kind of concept of lizard, something scaly maybe. In fact, this name does not help us at all. It's a name that we've applied to a group of organisms. So let's test our knowledge of what are dinosaurs, what are part of this group of organisms. So let's start with the softball one. What about this guy? And now I want you to raise your hand. Is this a dinosaur? Oh, I see. Come on, a little higher with the hands. I can barely see out there. All right. Good job. All right. What dinosaur is this? Stegasaurus. I don't think I need to give the rest of this talk. All right. Let's see the next one. All right. Is this a dinosaur? Oh, so the hands are waffling. I got some hands, I got some no's, I've got some knowledgeable people in the audience. So let's keep going before I give you the exciting conclusion here. How about this dude? Is this a dinosaur? Man, so many knowledgeable folks. All right, let's go on here. What about this one? Oh, the crowd's divided. All right. And this guy? I got a lot of yeses out there, and I got a lot of hands that aren't up. I don't know. Is this a dinosaur? All right. Well, in fact, our only two dinosaurs out of that group are the chicken with the shotgun and Stegasaurus. Now, I don't know about the shotgun, and we're not talking about accessories in the dinosaurian world here, whether they have little man bags or whatever. But what we are going to look at is, okay, so these are dinosaurs. Those other really awesome animals, including the one on the t-shirt, not dinosaurs. In fact, the guy on your t-shirt is more closely related to crocodiles, right, than to dinosaurs. Now, it turns out crocodiles and dinosaurs aren't exactly in vastly different pieces of real estate in the tree of life. Well, what it comes down to is that dinosaurs, this group of things, why some of these animals are called dinosaurs and some aren't, comes down to the fact that Dinosauria and dinosaurs are parts of one particular branch of the tree of life. And if you're not on that branch, then you are not called a dinosaur. So there might be some closely related branches there, but those are separate branches and not what we call dinosaurs. So if we look at the tree of life, we're on one particular branch, and dinosaurs are on another. And to look at another way of representing this in a kind of kooky circular tree format, dinosaurs are one tiny, tiny twiglet that actually, a twiglet off of that twiglet is living birds. So that one twiglet turns out is close to the twiglet including crocodiles. So crocodiles are the nearest branch to Dinosauria, which includes birds. Now, why does all of this matter? And how did we figure out this particular address for dinosaurs in the tree of life? Well, first of all, it matters, as I'm going to come back to, because we have to know where dinosaurs go to figure out something about their appearance. That turns out to be central. And how did we figure out this particular address? I mean, it sounds like there are a lot of knowledgeable people in this audience, so I'm not going to spend a lot of time on it. But just to basically, in a broad overview, for about 170 years, different scientists have noted similarities between birds and extinct dinosaurs. And that's in all of these bony features, all aspects of their skeleton and their skulls and their tails and in their legs. Any part you can imagine, basically there are shared kind of unique characteristics that locate birds with these extinct dinosaurs. Now, in the early 20th century, actually one particular researcher got together all of this evidence, and he saw all this evidence. He said, there's one problem. I can't find a wishbone. I can't find a wishbone in one of these extinct dinosaurs. I mean, this other Julia can easily find them in any, rotisserie bird. You can find them. I said, I've got all this evidence that birds are most closely related to these extinct dinosaurs, but I don't have a wishbone. Well, in fact, now we have wishbones, another piece of evidence. Just in maybe the last 10 to 15 years, we found them in a whole bunch of different dinosaurian taxa. And taxa is just a fancy word for a named group of organisms. But we found them in a lot of different dinosaur species, including very early dinosaur species, things that are about 230 million years old. And not only that, this character that you can find in your rotisserie chicken is in an animal 230 million years old. It's in tons of dinosaurs, including ones that people like a lot, like T-Rex. Anyone, their favorite dinosaur? T-Rex? I see it. Oh, there's a lot of people who like T-Rex out there. All right. So now we've accrued all this bony evidence to locate not only recognize that birds are most closely related to these extinct dinosaurs, but specifically locate them within the dinosaurian family tree, that locate that little twiglet that includes birds. And what we find is that animals like Velociraptor and Troodon and Oviraptor, and if that's too many names for you, I'm sure there's a lot of people in the audience that are into the... How many of my younger members of the audience are with me here? Troodon. Whoa, all right. So we've located birds in this particular part of the dinosaurian tree where we have Troodon and Velociraptor and all of these guys. And a little further out, we find T-Rex. And even further out, we've got our dinosaurs like Stegasaurus and Triceratops, etc. So we've found this particular position for birds in the family tree of dinosaurs. Now, we know all of that, but we also know that the other living cousin of dinosaurs are crocodiles. And we've had this thought all along, well, if we know where birds go and we know crocodiles are their nearest cousin, how does that influence how we think these animals looked? Were they more scaly? Were they feather-covered? Were they brightly colored, or were they more dull greens and browns? I mean, we've known where dinosaurs go, and that's going to become important to our story this evening, but we didn't know, it doesn't tell us everything we want to know about what they looked like. So, in fact, we were helped along in this understanding of what dinosaurs looked like by a bunch of key discoveries made starting around 1996. And if you saw Jenny's presentation, this is a 2-minute repeat here, but I want to show a little footage, basically move back into the Technicolor realm to help tell a little bit of the drama of the story of how our vision of dinosaurs was changed by new fossil finds from China.
Sometimes, ordinary people make extraordinary discoveries. A shepherd stumbled on the Dead Sea Scrolls. Teenagers found the cave paintings of Lascaux. And in 1996, with one swing of his pick, a Chinese farmer revolutionized our understanding of the dinosaurs. His blade struck an ancient rock. Inside, the fossil of a peculiar turkey-like creature. It was clearly a dinosaur, but the imprints in the rock showed strange new features. This dinosaur was covered with what looked like feathers.
There was a buzz, there was like a rumor that feathered dinosaurs had been discovered in northeast China.
The find sent shockwaves through the paleo world.
An astonishing discovery that will forever change what we thought we knew about dinosaurs.
Immediately upon seeing it, we knew that this was really a smoking gun, but totally unexpected and something we never would have believed we would find.
The new discovery, named Sinosauropteryx, was about 2 feet tall, with a small head, teeth of a meat eater, a long tail, and primitive filament-like feathers. These feathers could only be seen because of the rare conditions under which they were preserved. A volcanic eruption buried the creature in soft ash, locking in all its secrets before it could decompose. And it wasn't the only one. The find kicked off a dinosaur gold rush in the region. Over the next decade, hundreds of feathered dinos were found. and paleontologists began piecing together theories about what the feathers meant. They forced an immediate shift in our perceptions of dinos. What they looked like, how their bodies worked, and how they behaved.
All right, you guys still awake? Are you even more awake? Oh. So I have to point out that that's one artist, every time we see one of these dinosaurs, and I'm going to come back to it, but these are dinosaurs brought to life. So they always involve a collaboration between scientists and artists. So we're going to see a little more of that later on. But to come back to the story and make it a little clearer what I was talking about, when I talk about this buzz, I'm talking about a particular moment in 1996. How many of you guys were not born in 1996? Don't answer that. But in 1996, I was a graduate student, and I was at a research conference, and there were people passing around photographs, really crappy printouts of pictures of what looked like feathered dinosaurs. And there was a lot of disbelief, but a heck of a lot of excitement, because where these dinosaurs were closely related to birds, and it made it all the more kind of compelling and believable for that particular moment. Anyway, I was a grad student starting to work on the origin of birds, and this not only changed my career, but I can say it changed our view of dinosaurs, and really is continuing to revolutionize our understanding of them. So the fossils, just to quickly mention, come from quarries like this. And the way you find them is basically open a giant pit. And inside, you might split open a rock, and it opens like a book. And you'd see 2 pages of the book, ideally. And the fossil would be preserved in those sediments. So you would, crack these things open, and you might find an insect, or a fish, or a plant fossil, or you might find a feathered dinosaur. So in 1996, this was the fossil that we just heard about, and just to give you another glimpse of the kinds of structures we're talking about, but they were hollow filaments. They were kind of like the quill of a feather without the fluffy parts. In fact, I have one in my bag if Jay wants to. There's a, well, don't dig through that. I'll go get it. But anyway, they were hollow filaments that were like the center or the quill of a feather. And what was really striking was that not only did we just have this one find in 1996, but as the movie talked about, we had a whole new set of players come on the scene. Dinosaurs like Dilong, which is sort of a pony-sized tyrannosaurid relative, that also had these filaments, these hollow, quill-like filaments that were seen in Sinosauropteryx. And we had other finds. I'm just showing a couple here, like this guy who's an early relative of Triceratops that shows these bristle-like structures on the tail. And all of these fossils, as they're being found, are starting to paint a richer picture of what's going on. And finally, very, very recently, in 2009, we've got fossils of an early ornithischian dinosaur, so that's one of the ones I said slightly more distantly related to birds, that shows all of these filaments. Again, what we think might be proto-feathers or precursors to the kinds of feathers we have in living birds. And what's really exciting about this is that just since 2009, the possibility that all dinosaurs had some filamentous or bristles has really become kind of a realistic idea, something that's a serious hypothesis that all dinosaurs might have had these bristle-like structures. Maybe they had scaly parts. We know they also had scaly covered parts as well, but it's really kind of fascinating to find these new evidence that perhaps we have filamentous coverings in lots of dinosaurs. Now, my work focuses on close relatives of living birds. And by that I mean anything from your kind of velociraptor type dinosaur up through penguins, parrots, and things we have today. So what we found in dinosaurs that were more closely related to birds, we found feathers that were more closely related to bird feathers. And so this is one reconstruction of a Chinese dinosaur showing this remarkable feathering. So this is a specimen of Microraptor, which is an early relative of Velociraptor. So the same group of dinosaurs, they're called Dromaeosaurs. And you have feathers on the hind limb as well as on the forelimb. These feathers that are remarkably preserved and show in fine detail that we not only at this point have the quill, but we have the barbs and the little tiny barbules that make if you held it up, recognizable as a feather like that which we have in today's birds. So I've been working in China since 2000, and this was my primary collaborator in the middle. And we've focused a lot on fossils like this that are birds from the same deposits as the feathered dinosaurs. So going up, and what we found in these fossils was the same kind of feather structure. So not only are we seeing these structures in non-bird dinosaurs, we're seeing them in bird dinosaurs as well. And that makes it all the more a complete story. So with these fossils, we've been able to gain a lot of insight into the evolution of bony parts of the anatomy of birds. So how was the wing assembled? And also feathery things. So how did feathering change? How did it shift? Were leg feathers part of the evolution of avian feathering? Did they go through a stage where they all had long leg feathers, etc.? So these were some of the stories that we've gained insight into by these new fossils. So here is one vision, a very skeleton-ocentric view of one of these animals where we've focused on all of those bony features that tell us all these important things about the evolution of birds. And then we had a picture till about 2 years ago, or maybe even, I guess, a year ago, of these dinosaurs that's sort of black and white. It's gray. We know the distribution of feathers on the body. We can get a more realistic picture of what their shape might have been, where the feathers located. But we're not getting a picture of the patterning, right? That's really going to be key to seeing what these animals were like. We have a lot of visions, new visions of these dinosaurs. So we have visions of animals with combinations of bristles and more anatomically modern feathers, and visions of scales. Incredibly exciting, but none of that really, the coloration, constrained by any kind of scientific evidence. So we're, prompted to ask the question, how would then you figure out the color of an extinct dinosaur? I think we never even, most of the paleontological community never thought we could ask that question. Maybe that was a question we couldn't get the answer to. How many of you guys have ever asked a question at a lecture like, how do we know what color that dinosaur, like how many of you have wondered about the color of dinosaurs? Yeah, I wondered, but I never thought we would be able to approach that with data of any kind. Well, it really was, let me go back to that. I want to set this up. To figure out, however, what colors dinosaurs might have been, we clearly are going to have to look to the living ones. So any insight that's going to be gained is going to have to be through looking at these feathery structures and how these feathery structures are colored in living birds. So if we look at living dinosaurs, they color their feathers in a whole variety of ways, using different kinds of pigment and also using what we call structural colors, which involve tiny nanostructural or microstructures of feathers that refract light in certain ways. Well, we're not going to go into all of those today, but we're going to focus on one mechanism by which birds color their feathers. And that mechanism was we found, let me step on to the next one. So it's because that mechanism we have evidence of in the fossil record. And so this goes back to a discovery by Jakob Vintner, who Jenny talked a lot about, and his colleagues, who published a paper in 2008. And what they noted was that in fossil feathers, which we knew had these patterns like this stripy pattern where you can see, can you guys see the dark and light, dark light? So we had these fossil feathers, we could see this pattern, but no one really knew what that represented. Was that leftover carbon from the degradation of these things? In fact, we still don't have a lot of answers to that. But by taking a closer look at these feathers, Jakob discovered that the same pigment packages that color living feathers are seen in these fossil feathers. And he was specifically looking at melanin because, based on his research with the squid, he knew that melanin packages called melanosomes could be preserved in the fossil record. And this is a major, major insight. Now, melanin, I'm going to come back to in a moment, is actually what colors our hair and what colors a lot of different types of bird feathers. So at the top here, we have the structures that Jakob recovered in the dark areas of this feather. And in the middle area, we have the white area, or the light-colored area, where it shows no melanosomes present. So we have these imbricated, tiny, tiny sausage-shaped packages all lined up here, and the same kind of structure you would find in a living feather. So if we look at this particular feather and you were to cut it open and you cut open the dark section, you would find a whole array of what we call eumelanosomes. And then in the white areas, you'd find melanosomes to be absent. Now, how do we translate that knowledge that these packages of melanin can be preserved in fossil feathers into knowing about dinosaur color? Well, first we have to understand what these packages really mean and what data can we get from them. And to do that, we can turn to our understanding of melanin more generally. So the melanin that you have and that birds have in their developing feathers is of a similar kind. And what happens in the developing hair is that melanin is pushed into the developing hair or the developing feather in little packages called melanosomes. And it turns out that the shape of those melanosomes is related to the chemistry of the melanin that they contain. Okay, that's a lot of stuff that may seem a little too detailed, but overall we can look at this and say that black hair has melanosomes, eumelanosomes, that are more elongate in shape. Red hair has melanosomes that are more rounded, and gray hair, for example, has relatively few eumelanosomes. So we could relate the shape of these melanosomes and also, so this is data on mammals. Let's turn to birds. The same thing holds. If we look at rusty brown colored bird feathers that are colored by melanin and not some other pigment, those feathers show these rounded phaeomelanosomes which create brown and rufous red colors. Whereas if we look at black feathers, they're created by these eumelanosomes, or sort of sausage-shaped melanin packages. And it relates to the chemistry of the melanin contained in them. And then in the white feathers, melanosomes are absent. So this is a start, right? So if we know that the shape relates to the chemistry, relates to the colors that are produced, then, and the shape is preserved in the fossil record, well, maybe we could get at some way at the color of dinosaurs in this melanin-based coloration palette. I want to give one extreme example because we have this much reviled member of Dinosauria in Austin. And here we have an extreme example. These guys have eumelanin packages in the developing feathers that are actually so thick and organized in a particular way, they create this glossy shine. It's a black color with a blue glossiness. And in fact, we've found some evidence that we can see iridescence, or the same kinds of colors we see in grackles, also preserved in the fossil record. But I'm not going to talk much more about that today because we're headed right now to China. So our team is assembled. I think I must be still digesting our large lunch. Here we are with the gentleman that found the first feathered dinosaur. But we're heading to China because that's where we would need to bring these new tools and look for the right kinds of fossils to answer our questions. And we went to museums all over China looking for specimens that preserved incredible feathering, but also were not coated in glues, were not fixed up to look really nice. We needed something that we could sample to look at microscopically that wasn't much affected. So we got really lucky. We were in the basement of the Beijing Natural History Museum, and they had just gotten this fossil in. And it was remarkably feathered. I mean, one of the first things you notice are all of these feathers. But it was still wrapped in newspaper, and we didn't know what this animal was. But it actually turned out to be an incredibly well-preserved skeleton, including the skull of a newly named dinosaur that at that time had been named mere months before, called Anchiornis huxleyi. So named for one of the people who first noted the evidence that birds are most closely related to extinct dinosaurs. So this was a truly phenomenal specimen. And really what caught our attention were all of the apparent color variation in these amazingly preserved wing feathers. And even in the foot here, with feathers extending all the way down to the tips of the toes, we have regions of dark and light. Was this evidence of color patterning in the feathering of this dinosaur? So here in the skull, we had what looked like a crest, potentially a crest, but would we be able to tell anything about the color of that crest? So we sampled all over the specimen. Thankfully, we were able to take these tiny, very, very tiny samples from all over the feathers, some within different feathers, and all over the regions of the skull. And these are examples of some of the samples. And what we can see immediately is we have more rounded phaeomelanosomes associated with rufous red coloration mixed in with some eumelanosomes, and eumelanosomes of varying densities, so how many of them there are there. Well, we looked at a lot of samples. We took 29 samples from all over the animal, and we got all this data. And we could see a lot of eumelanosomes, the round ones and the long sausage-shaped ones. But how do you translate that into a color map? Because living bird feathers, sometimes there's a mix of reddish or a lot different combinations of these. So it took a library. It took a library of samples of living bird feathers that are colored by melanin, and they're of known color, and we can look at the density and the shape of all the melanosomes in those samples. And building this large library allowed us to take the samples from the fossil and compare them to the samples from living birds. No one had done this before. And so these individuals in the lower right here are not part of our sample. They are, in fact, my colleagues that really developed this library and worked with the rest of the team on the methods, figuring out the methods for doing this. So with this color map, we took all of these individual samples that are shown in red and blue and came up with this. And this took a lot of back and forth with the artist, because there's still an artist involved here. I mean, we're still making a reconstruction of this extinct organism. But we had a level of detail that no artist has had to deal with. A bunch of scientists saying, well, this millimeter over here needs to be gray and then black. So I'm not sure they were totally happy with us. There was kind of reining in what their role could be in interpreting this data. But we actually had details of the feathering going all the way to the tips of the toes, gray. We had the spangles where we have blacks and whites. on the tips of these feathers, and evidence for both gray and red on the crest and the head of the animal. So, you know, there's kind of a gee whiz factor here, right? So there's like, wow, you know, for once, this is an animal for which we had data to really speak to most of the parts of the body. We don't know exactly how red, was the whole crest red or part of it, but in more detail than we've ever had for an extinct organism, we got this picture. So, is it just gee whiz? What can we do with this kind of understanding? Well, what struck me when we started looking at the data was that if we looked at all the feathered dinosaurs out there, and we looked at all the ones that had this feathers that look like living bird feathers, as soon as they show up evolutionarily in dinosaurs, they're patterned. I mean, from the data from Anchiornis, where we have patterning within individual feathers, and we have other dinosaurs where we can see suggestions of that, like we can constrain, and by suggestions of that I mean striping in rocks that we know preserve very fine detail of the feathers. So there's actually another dinosaur, an oviraptor, that has striped feathers. We've not been able to color map that dinosaur, but that's one of the pieces of evidence that we used. So the point being, and the point to take away from this, is that as soon as we see these anatomically modern feathers, the dinosaurs are not flying, but the feathers are patterned. And this was really cool, because, well, let's look. So I have to keep moving away from the mic, but if we see this patterning in feathers before the origin of active flight, what is the implication of that? Well, in living dinosaurs, communication and signaling are a key role for feathers. And feathers obviously also serve many important locomotor functions or functions in different ecologies. But what this suggested is that feathers at their first origin might be involved in not the proto-feathers, the little filamentous guys, we don't know totally about them, but when you see an anatomically modern feather, as soon as they appear, they're patterning these animals. So it gives a primacy to the function of communication, attracting a mate, sexual selection of feathers in the history of dinosaurs that we've never had before, which is really cool, I think. And in terms of our implications for how we've seen these animals, this is a reconstruction of Anchiornis, the same dinosaur you just saw a picture of, from before the color mapping. You can see how the colors are envisioned as involved in camouflage in a woody habitat. Here's another one. This is a Microraptor, another feathered dinosaur reconstruction. And you see again, the feathers are envisioned as related to camouflage. So, if we look at our animal, we see these large color patches. We see the red crest. They're things that again come back to, at some significant importance, to communication and signaling for these early feathers. Something more like this guy, where we have bright patches of coloration on the wing and a distinctive crest, something more than camouflage. So I am going to wrap this talk up a little bit with just looking at how far we've come and what this sort of means overall. What does this mean for paleontology as we move forward, and for our visions of dinosaurs in Technicolor or in print, etc. So we've gone from this picture by knowing what a dinosaur is, knowing they're a particular branch of the tree of life that includes birds and is closely related to crocodiles. From knowing that, we've been able to get a much better picture of what dinosaurs look like. And by knowing what a dinosaur is, where it goes in the tree of life, we've been able to discover, through looking at living dinosaurs, this way of figuring out color patterns in extinct dinosaurs. So it really is moving from these lumbering lizards with, just choose your colors here, purple, green, blue, just choose whatever you like, to having an informed sense of what these animals look like. And that gives us insight not only into the evolution of feathers, which is a major transition in the history of life, but it also gives us insight into the biology of these animals. And I've been particularly interested in that because a little bit closer to my heart. I don't know, these guys are pretty cool, but giant penguins, they're also pretty cool, right? No, I've got too many non-avian dinosaur enthusiasts in the audience. But these same methods we employed earlier this year to look at giant penguin coloration. We were lucky enough to find an amazing giant penguin with beautiful feathers, and were able to do the first color map of any extinct bird. And what was really cool was that we found out, and I'm not going to go into this now, but we found out that living penguins, by looking at a fossil, we discovered that living penguins use color mechanisms, or particularly giant melanosomes, actually, to produce really common colors. And we never would have asked that question of living penguins if we hadn't been asking questions of this fossil. And in fact, what we found was that at least some early penguins looked quite different. We have no evidence for the tuxedo shape, but we have dominantly grays and even reddish browns in these in one giant penguin from low latitude regions. So with that, thank you for your patience, and indulgence in coming out on a Friday night to listen to me talk. Thank you, and I'm welcome. I would love to take questions. So thank you very much.
So if you do have questions, we have these mics. We ask you to come up to the mics and line up and ask questions, and Julia will pick you. Can you see them okay?
Sort of. I can see someone over there.
You're either there or there.
Okay, I'll just point randomly. All right, let's start on the left.
Before we knew that there were color in dinosaurs, did we know whether dinosaurs could see color?
That's a very interesting question. Because of dinosaurs' place in the tree, we do believe that they would have inherited from an ancestor an ability to perceive coloration. And some of it is also, there's a difference between perceiving patterning and perceiving, different ranges of coloration. So I don't know that we know what exact range of coloration or would have been able to reconstruct that, but there is some evidence that because of their place in the tree of life, they would have been able to perceive color.
Okay, and one more. Is there any evidence that there are any blue dinosaurs?
Any evidence for blue dinosaurs? Well, it turns out that a lot of blue coloration in living birds is created by what I called those nanostructural or microstructural aspects of feathers that refract light. So they're actually like, you might think of them in some ways like a prism. So it'd be very difficult to preserve that kind of organization to be able to figure that out in a dinosaur. So the answer is we don't know if there were any blue dinosaurs yet. All right, over there to this side.
Hi. As we see in birds, there are often stark differences in coloration between male and female. I was wondering if you'd found any evidence of color maps within the fossil, that there's a difference between male and female in the sexes of these dinosaurs.
Yeah, that's a really great question. No, because we've only done one color map for an extinct dinosaur, but we've thought about that question, and I think that's certainly where research is going to go. For some species, we have multiple exemplars, multiple specimens, so one might be able to look for plumage differences. Now our problem is going to be, are they male and female? Are they juvenile, adult? You know, figuring that out is going to be potentially tricky. But it is a question that I think people want to ask.
Okay, thank you.
Yeah.
I'm wondering if ostriches could be related to that type of dinosaur you said with feathers.
Well, that's a very good observation. Ostriches, because they're part of living birds, are related to the other extinct dinosaurs that we just talked about. So they're just one other little twiglet in that whole branch that we call dinosaurs. And ostriches, it turns out, are one of the early branches in all living birds. So they're pretty cool, and they do lots of crazy stuff with their feathering. So they're a great animal. Do you like them?
Yeah.
Me too. I'm a fan. Thank you. I think we'll go over to that. We'll switch sides. Yeah.
When you cut open a part of a feather that's white, is there always melazone? Is there ever it inside it?
Well, that's a good question. So I think that in some white feathers you might see melanosomes in very, very low density, so sort of like gray hair. But typically they're not there. In white feathers you would not have melanosomes. So I guess the answer to your question is yes. I don't remember if it was, does that answer your question?
Yes.
All right. Okay. All right. Okay, back over here.
I can see how dinosaurs like Tyrannosaurus rex and Velociraptor are connected to birds, but I can't see how Stegosaurus and Triceratops are.
Okay. So what you could think about is that, you know, your mom and dad are more closely related to you, but then you have some cousins and some slightly more distant cousins. So Stegosaurus and Triceratops are kind of like your more distant cousins. But they're more closely related to birds than they are any other group of living animals. So they're just a little bit more distant. Does that help out at all?
Yeah.
Okay. All right, back over here.
Could dinosaurs be warm-blooded like birds are?
Well, I think that we believe, basically, the evidence that we have to date suggests that a lot of dinosaurs, and maybe even more than that, had some kind of intermediate physiology. Like, it's not as black and white as cold-blooded and warm-blooded. There's lots of different physiological aspects, like how fast you grow. It's related to what your metabolism is. There are all different aspects of physiology there. And I think the consensus would be that most dinosaurs have physiologies more closely related to birds, you know, than anything we see in extant crocodilians today. So I think especially in dinosaurs that are very closely related to birds, a lot of people think there's some degree of warm-bloodedness. But it seems to be a more complicated question than that. So I hope that is a sufficient answer. Science is a process.
Okay. Thank you.
Yeah. Okay, back over there. There's one in the... Is there a mic in the back?
Yes.
Oh. Oh, I'm sorry. Okay, back in the back over there.
Is there any evidence for feathers in sauropods?
Okay, so are there any evidence for... So basically, the feathers that look like things we see in living birds that have a central quill and barbs coming off of them, we only know those in really comparatively close relatives of birds. And the filaments seem to be more broadly distributed, but as yet we have no evidence of them in sauropods. And not only that, we have evidence of some sauropods having scaly regions on the body. So we know that at least some sauropods had significant scaly sections to them. Same with ornithischian dinosaurs. Okay, does that help?
Didn't you say that ornithischians had filaments?
Yeah, so the thing is, even in that dinosaur I showed, that one that's kind of an early part relative of Triceratops, they have scales on some parts of the body, and they have the bristles on the tail. So when I say that maybe all dinosaurs had filaments or bristles, they might not be covering the whole body. And so it seems like in certain animals, they're not. So to know whether a sauropod had any of them, you might need to have most of the sauropod with skin on it. So I hope we find one of those. Pretty awesome. Yeah. All right. There's another one in the back over there on the right, I think. I don't know. Do you want to adjudicate this? Because I can't really see very well. Okay. Oh, look, the guys in the front?
What are you laughing at?
Viewpoint.
Why?
Who's been waiting? Okay, just somebody ask a question.
I have two questions. First one, how do you tell if a dinosaur is a boy or a girl?
How do you tell if a dinosaur is a boy or a girl? You know, with living dinosaurs, it's pretty easy. And I'm not going to explain that one. But, you know, with extinct dinosaurs, you're going to have a lot harder time with that. Sometimes we get extraordinary glimpses into past behaviors through, you know, their added the preservation in the rock record. But we still don't know. Even the nesting dinosaurs, so we have dinosaurs now that are sitting, brooding a nest. But there are living birds where the males brood the nest, and there are living birds where females brood the nest. So we can't even use that as an indicator. It's very tricky to figure out.
All right, and then what's your favorite dinosaur?
What's my favorite dinosaur? I don't know. I kind of move around with that, but it's usually some bird that people aren't that excited about. I mean, I tend to like real outliers. So right now, I would love to have a pet flightless rail. I don't know if anyone knows what that is, but they're really awesome. They're very cute. They can't fly. Anyway, great pet. They would make great pets. So I don't know. I like a lot of dinosaurs. I'm in the right job. Okay, next question. Those guys in the front over here, Texas.
I have a reptile book that suggests we may have been descended from a family tree of reptiles that evolved to have fur and live birth. Do you think that is possible?
Well, in fact, you know, one of those guys that I asked you about, like, what is a dinosaur? One of those was more closely related to us. So, you know, if you were to look at this dude right here. This is an early relative of us. Oh, it's blue. Well, just take my word for it. The sailback guys you get in your little dinosaur packages are typically not dinosaurs, but they're typically included in your little bag of dinos. I don't know what I need to do to make it not blue, but oh, there you go. This guy, more closely related to you than a dinosaur. So I hope that answers your question. All right. The question from the internet. Boy, this is taking it out of the Jurassic here. All right.
Yeah, so before we do that, I just wanted to let you know that we're going to be, shortly after the questions end, we'll be raffling off some door prizes. And those of you who have bought one of these T-shirts, Julia would be happy to sign them if you're so interested. Okay.
I'm happy to write on there, this is not a dinosaur.
And you would be one of the few people to know that correctly. So this question comes from Garicki Middle School, where they're watching on the webcast. And the question is, Dr. Clarke, do you believe you'll be able to map some of the larger feathered dinos in the near future?
All right, great question. The tools are there. At least for looking at melanin-based coloration patterns, we should be able to do it. So it's a question of who's going to let us take tiny samples of their large feathered dinosaurs. It's an important point. And also finding ones that, you know, do a color map, you really need to have a whole region of the body. You really need to have a bunch of different samples to get at the picture, not just in one region of the body, but over as much of it as possible. And some of the larger feathered dinosaurs, although there's some new ones that are pretty complete, there are not a whole ton of them. So the tools are there. I'll end with that. Yeah.
Yes, go right ahead, right there. You're next.
Here?
Yes, you.
Are all the all the birds in the entire world that are alive, are they all related to dinosaurs?
Yes. And there are around 9,000 species of living dinosaurs, birds, around today. And all of them are descended from a common ancestor that's actually not terribly old, but goes back to the age of dinosaurs. So the simple answer to your question is yes, they are all on one little branch within this larger branch we call Dinosaurius. So they're all related. Great question. All right. In the front over here, I know there's some people on the right too. Okay, yeah, next.
Did a alligator live at the exact same time as dinosaurs?
Yes. Not any living species of alligator, but early relatives. In fact, we have two experts, I think, in the audience, I don't know where they are, that work on early relatives of crocodiles and alligators that were around the same time as the dinosaurs. And in fact, we know in some cases they chewed on their bones, as my grad student works on. I think he might have left. Okay. All right. Yes.
Did dinosaur? How do you call a dinosaur's skin? How do you tell its color?
Okay. Well, how do you tell the color of the scales? So you could use the same approach as long as those scales were colored by melanin. So you would take a similar approach to that with scales. And in fact, these things we have on our toe, our fingernails, our claws, they actually can also be melanized, so you could look at the color of them by using the same technique. Maybe more info than you wanted. But, okay, on the back right, I think these guys have been waiting over here. Yeah.
I have several questions. Do the bird bones back then have similar density to birds' bones now?
In terms of how dense they are.
Weight-wise.
Earlier birds tend to have thicker cortices, so in general they have slightly more dense bones. But frankly, it's not really a huge difference. These are all hollow-boned animals. In fact, hollow-bonedness actually goes really deep within dinosaurs. It's reversed several times. So, yeah, they tend to be a little bit thicker, but not a huge amount.
The other question is, did the bird bones back... Did the birds back then lay eggs like now?
Did they lay eggs? Well, egg laying is a primitive characteristic that actually all dinosaurs inherited from their common ancestor. And so actually all dinosaurs, including birds, laid eggs, and they inherited that from a common ancestor. Now I'm going to move on to another person, but I hope that's good for the questions that you've asked. All right, blue shirt.
What effect, if any, did the discovery of feathered dinosaurs have on the evolutionary debate between gradual progression of evolution versus a more punctuated view of evolution?
So it's a really great question. What we see, I don't know how much debate I really think there is nowadays. I feel like we're asking more nuanced questions because sometimes it seems like, during certain periods in Earth history, there seems to be a lot of change going on, and other periods of Earth history and other groups, less. So, in fact, both are right. During certain periods and groups of organisms, there's a lot of change happening pretty fast, and then in other groups might be slow and more gradual. What I find working on bird origins is that we have very, when we get more fossils, we see more gradual accrual. So it was sort of like we saw these bigger jumps, but it was because we didn't have the fossils to fill in that part of the story. And really, you could think of feathers as a great example. You know, now we have like early proto-feathers, and we don't see jumps because we're sampling more animals there, more fossils. So in that sense, basically we perceived jumps where there were really, it was really more gradual once we got the data. Okay, I think Jay's going to tell me we're almost out of time, but I'm happy to stay around. We'll take like...
She's been waiting a long time.
Okay, we're gonna go over here, and then I'll stay around and talk if you guys have more questions. Okay.
Okay, so do the bones of the dinosaur tell you the color of their feathers also, or not?
So no, the bones are not. Basically, just like our bones today, you know, they're inside, and so we've got all of the skin on the surface that's going to contribute to our color, you know, or what color we would be perceived as, and our bones are mostly hidden. So we use the feathers that are covering the animals to look at color patterns in their plumage.
Okay. Also, at the end, can you sign this sheet of paper?
Yes, happy to sign any well, I won't say any sheets of paper. Okay, so in the front, purple dress.
Do dinosaurs change colors when they eat something different?
You know, you've asked a very smart question. So some living dinosaurs, like a flamingo will be a brighter pink if it's consuming more food that has a lot of keratins in it that are going to give it its bright pink color. And it's going to be a little lighter colored if it's not eating those things. So we can't look for keratins yet in the carotenoid pigments in the fossil record yet, but if we could, we might actually see those kinds of differences. So it's really a great question. Think about flamingos. They are dinosaurs that change color depending on what they're able to eat. So, in a very broad sense. Okay.
Well, here's what's going to happen. We're going to raffle off some door prizes. Julie's agreed to, those of you who come up to the front, ask some questions. She'll continue to answer them while we're raffling these door prizes off. So let's thank her once again for her amazing presentation.